If there were a competition for the most useful distribution, that's over. The normal distribution won it in a landslide. However, we could have a pretty active discussion about what deserves second place. The Poisson distribution would certainly be in the running. At any rate, the Poisson distribution is used to model counts. The Poisson mass function is lambda to the x, e to the negative lambda, all over x factorial, where x is defined on the non-negative integers, 0, 1, 2, and so on. The mean of a Poisson random variable is lambda, this parameter here, and the variance of this distribution is also lambda. So that's an interesting thing to take into account when you model things as if they're Poisson. The mean and the variance have to be equal, which if you have repeated Poisson data, this is a checkable assumption. I'd like to give some instances where we use the Poisson distribution. Anytime you want to model count data, the Poisson distribution is a candidate, especially if those counts are unbounded. There's also another set of data that's very common in the field of biostatistics, so-called event time or survival data. So for example, in cancer trials, you might be trying out a new therapy. You would model the time until people have a recurrence of some symptoms. Some people may not ever have that recurrence, and some people may in the time of the study. You need special statistical techniques to deal with that problem of so-called censoring, and those techniques have a deep connection with the Poisson distribution. Whenever you take a sample of people and you classify them according to some characteristic, for example hair color, and just look at the counts of the people of various hair colors, that's called a contingency table. You can create cross-classified contingency table if, for example, you were to count hair color by race, and each cell would be the specific race hair color combination, the count of the people in the sample that had that specific combination. The Poisson distribution is the default distribution for modeling contingency table data. And it turns out that it has, again, a deep connection with some of the other models you might think to use, such as multinomials, binomials, and Bernoullis. A final instance where the Poisson is used, and this is done so commonly it's not even really stated as people are doing it, is in instances where you have a binomial, but n is very large and p is very small. This, for example, happens very commonly in the field of epidemiology. My friend Roger studies air pollution, and he looks at, as air pollution rates rise and fall, the number of new cases of, say, respiratory diseases in large areas, like cities, for example. Well, the n is very large, the population of the city, but the number of events that he's looking at are often quite small. And so he models those as if they were Poisson. And this is done so commonly in the field of epidemiology that people don't even really say when they're doing it. They just do it and everyone knows what they're talking about. The Poisson distribution is often used to model rates. So, for example, let's let x be Poisson lambda t. It's important to note that lambda here has units. It's the average number of events per unit time where t is expressed in that particular time units. So lambda is the expected count per unit time, and t is the total monitoring time. So this is a very common use of the Poisson distribution for modeling rates. So imagine if the number of people that show up to a bus stop is Poisson with a mean of 2.5 people per hour. We watch the bus stop for 4 hours. What's the probability that three or fewer people show up the whole time? So that's just the Poisson probability of 3, 2, 1, and 0. And the rate we want at this point is not 2.5 because it's 2.5 events per hour, but we watched it for 4 hours, so we want to put in a rate of 2.5 times 4, and here we get the probability here of 1%. Let's talk about the Poisson approximation to the binomial. Particularly when n is large and p is small, the Poisson can be a quite accurate approximation to the binomial. To tie down notation, let's let x be binomial np and define lambda as n times p. But here we're considering circumstances where n is very large and p is very small. Then the proposal is that the probability distribution governing x, which is binomial, can be well approximated by Poisson probabilities with this specific notation, lambda as n times p. As our final example to discussing the Poisson distribution, let's go through a Poisson approximation to the binomial. So imagine if we were to flip a coin with success probability 0.01 500 times. What's the probability of 2 or fewer successes? This is simply to illustrate that I have a setting that's a binomial probability with a large N, 500, and a small p, 0.01. And now I want, but it's still in the realm where the binomial calculations are possible. So here when I do p binom for 2, because the question asked for 2 or fewer successes, size equals 500, 500 coin flips, probability equals 0.01, suggesting that the true success probability of the coin is 0.01, I get around 12%. When I do the same calculation with Poisson, 2, and then now instead of inputting the size and the probability, I put in lambda as n times p, 500 times 0.01, I get 12.5%, so fairly close.